and welcome to the Forecast Decision Training Division GO 16 application bi-weekly webinar. We're very happy this week to have Kevin Laws, who's the Sioux in Birmingham, talking about convection. That's a title I chose, Dispelling the Myth of Random Convection. And we'll be talking about that a little bit later. Just a couple of introductory notes. Kevin, if you want to go to the next slide. This is part of the FDTD satellite chat. There's a website if you want to look at previous topics. There's a whole list of topics relating to GO 16 and how you might use GO 16 in your workflow. If you want to talk about something, we're always looking for speakers. You can email either me, Scott Lindstrom, or Dan Bicus at NOAA.gov. And the next slide, please. We typically have about 20 minutes for the speaker. Kevin has a lot of slides. We'll see if he gets through all of them in 20 minutes. And then there's some Q&A, and we'll be ending by 18:30. Sorry, I didn't change that, so we'll be done by 18:30 UTC. Don't press hold. And if you're not talking, press your mute button. And take it away, Kevin. Thanks.
Okay, thanks, Scott. The genesis for this project that we started back in around 2009 was to, what I started noticing that a lot of our forecasters decided that they would take the summer off because the summer weather was easy across the southeast. We would forecast 90-something degrees for the highs, lows would be in the 70s, and every day you'd have a 20 to 30 pop. And you kind of get into this habit, and there's a lot of that across the East Coast and across the Southeast, especially, where you start to see this, what people were calling popcorn thunderstorms or random convection. And I sort of said nonsense to that. Back when I was at NC State in the 90s, Steve Koch and I worked on a project where across eastern North Carolina, with all the sounds and the inlets across the Outer Banks there, where we would notice that convection would pop up on these sea breezes during certain conditions, certain conditions they wouldn't. So we started working on this, and we all know the old rules of thumb that you need three things for convection to occur. You need the instability, you need moisture, which we always have across the South in the summertime, but that final ingredient is a lifting mechanism. So our goal here was to try to dispel this random convection, and the way we're going to do that is try to find these areas of lift. If we can find the areas of lift, then we can sort of start to dispel that myth that they sort of just pop up anywhere and everywhere that they want to. Second part of this was to sort of collaborate with research groups and research communities. In this particular project, we combined with NASA Sport up in Huntsville, and we'll get to that. So we wanted to be very methodical in our approach. We wanted to spend 4 summers really delving into this topic to see if we could change something from research into operations. So for summer 1, we really wanted to identify these boundaries to see if we could get a handle on what was happening. We didn't really want to get into the forecasting part quite yet. We just wanted to see if we could pick out some of these features. So we would start with an old school surface analysis by hand a lot of times. We would do this every single morning and put these things together, and we would start to identify different features across our area. We'd move on to satellite analysis because, the resolution of the surface analysis is just not quite high enough to get down to this really meso and sometimes micro scale that we really needed to look at. So satellite, which is where this talk is going, was a huge part of that and a major component. So from there, we would start to identify different boundaries from satellite. We'd move on to radar, whether it be the afternoon after the convection already started or that morning. And you can see quickly that this entire composite starts to come together. You see really how complex the summer was compared to, I guess, what our thought process was with this old school, what's the word I'm looking for? The old school notion that the Bermuda High sets up somewhere in the Atlantic and you have this southerly flow that impacts a lot of the south and east coast of the United States during the summer. Turned out to be a lot more complex than just that standard model that we had in our heads. From that study, this is really early on, we compared it to what Steve and I did in North Carolina, and we noticed that a majority of our boundaries that we interrogated were outflow boundaries, either from the previous day or the current day. We do have a little bit of topography here, which includes a sea breeze that comes up from the Gulf Coast, as well as some ridge tops. We have, I guess, I don't know if I'd call them mountains, but we certainly have some larger hills here in the northern parts of Alabama. Fronts, like synoptic scale fronts like you might expect, or troughs, are pretty rare in the summer. And then we had this significant component, about 10%, that was unknown to us, different boundaries that we would see that we couldn't really identify where they were coming from. Step two, summer two, I should say, we started to look at this first generation of convection. So where these storms would actually start to form, because you have this sort of a convective, almost a convective feedback kind of mechanism. Once you have a first generation of storms, outflow from those storms would generate other storms, that you would have boundary intersections and all kind of things that would happen there. So we wanted to just try to focus in on, could we figure out where this first generation was going to form. Again, we used that detailed analysis from GOES and NEXRAD. And this summer we also introduced the SPORT from NASA to help us with the land information system that lists data as a potential source for identifying those unknown boundaries. The list, just delving into a little bit more, it really looks at the land surface forcing. It takes into consideration soil type, soil moisture, the vegetation, land cover, albedo, and things like that. So you have these little moisture boundaries that form maybe from a previous day's convection where the soil maybe a little bit more moist. They set up a nice little website for us where we could look at their products on a daily basis. Here's an example. So Alabama has a very complex soil type, and in fact, that little area of green that you see there, that sort of a C shape, that's actually called the Blackbelt of Alabama. That's where the Gulf of Mexico coast used to come up millions of years ago. So there's a lot of rich agriculture in this area, and it's a different type of soil. So oftentimes we'd see these boundaries sort of form there. Same thing with the vegetation. Obviously the vegetation would change largely too based on the soil type as well. So these are the kind of things that we wanted to use to identify these unknown boundaries if we could. Here's an example of one of the products they would give us, like relative soil moisture. So they would, see my mouse cursor here, they would look at where there was previous day convection, and there would be these moisture gradients that sort of set up in little pockets, and those would be boundaries of interest for us as well, at least in the forecast process. And you see here from a visible satellite, you can almost sort of pick out that inverted C shape that we talked about here in the soil and vegetation type, and you can see where there is at least a convective process with the cumulus clouds sort of forming in areas that are not there as well. And you can also see the city metro area of Birmingham is up here where my mouse is pointing. And so that also is taken into account as well. So these little things, these little notions like this that we sort of pick up on helped us in the forecast process. Other boundaries that are sort of floating around, you can sort of see, I didn't want to get too much into the loops because of the bandwidth issues, but you can sort of imagine that these boundaries are sort of floating around. We would spend a lot of time in the morning, especially around sunrise, and sort of pick these out. These could be an old sea breeze boundary. The Gulf Coast is about 100 kilometers to the south, and these old sea breezes continue to matriculate inland even through the nighttime hours. Here's another old boundary as well over here that came in from Georgia. I think this was, in this example, was from a previous day's interaction with convection, and it sort of would be a trigger for us to focus in on with our forecast for that day. A lot of times these are not even, they may or may not be Rayleigh scatter. I don't know if you know what I'm talking about there, but you have a Rayleigh scatter with things like bugs that may be picked up. But the radars are also sensitive enough to pick up Bragg scatter too, which is like a turbulent motion. So they're a little bit different in terms. So it's kind of hard to say what those really are. If they're really bugs or some kind of Rayleigh scatter, or if it's more of a turbulent kind of deal going on too. So a lot of times as well, if you have convection that's out over, say, water, you won't see these kind of boundaries, because if they are bugs, which a lot of them are, especially in the summertime, bugs are smart enough not to go over the water, so you won't see these kind of features go over the water unless it is Bragg scatter. We also, everybody's sort of getting into the GraphiCast mode. This is early on, so they kind of look a little bit basic and maybe elementary to some, at least compared to the graphics they were doing now. But back in the day, we really wanted to put out this experimental because our philosophy here was going to be, hey, if we're going to spend hours doing this in analysis in the morning, we might as well make it go for something. So in an experimental mode, we started publishing these graphics I don't think we're on social media quite yet, but at least on our front page. And they really were very popular. We got a lot of email and comments about them, and people really did like them. At least tried to improve upon this idea of a climatology of 20 to 30% pop. So they were highly popular. I did include one loop. I guess this was kind of running in order. So we got those boundaries. We figured out where they would initialize, and this was sort of I don't know how good that's showing up on your screen, but you can sort of see where that old boundary was, where I had those arrows, one coming in from Georgia over here and the other one coming up like an old sea breeze from the south. And so those were kind of areas we focus in on. If I overlay over top of where that same image, this is kind of a mini case there, but the same image from the graphic cast, you can sort of see this is where we expected at least to have a higher pop, or where we would have raised pops on this particular day. Same thing with the satellite. Just wanted to throw that in there as well. You can see these kind of boundaries that we're setting up here. You can almost pick out here where that boundary was coming in from Georgia. It's kind of got that little concave shape there. You can see that coming in, so it's clearing out those lines behind it. So it's just further enhancing that lift between areas that would warm up faster than areas that were cooler. Same thing coming up from the south here into this part of central Alabama, that boundary that was coming up. I guess it may be an old sea breeze or whatever that we tried to identify from the day before. And again, a few hours later, you can see this convection firing up along those same said boundaries. See little angles that are peeking out here. So we're being quite successful in picking these things out and in our attempts to figure out where this first generation of convection would begin. By the end of the second summer, we start to get a little bit more comprehensive about the boundaries that we're identifying here. The back box plot here is the number of boundaries, and then how many of those verified. In other words, how many of those had convection on average with them. So most of them are convective because, like I said, in the southeast in the summer you already have moisture and instability in place, and so you can see a lot of these were, in fact, verifying at least convection on them. So we felt pretty confident if we could find them that they would have convection enough to at least change the forecast. Number three is when we really got into it and started working with an experimental, what we call an E-pop, an experimental pop, where we would compare the midnight shifts overnight package back in the package mentality days, where we have a 4 a.m. issuance of today's forecast. The morning crew would then come in and create an experimental pop that we would compare the two. So we'd compare what the midnight shift came up with, whether it be climatology or whatever, if they used a model output or whatever their idea was for the pop of the day. And then we would do this identification with the boundaries, not using numerical models at all, just our wits and identifying these boundaries. And we would compare the two to see if there was indeed any improvement. Also, the graphics started to get better, and one thing I really started to notice is that our forecasters here, especially the younger guys who were excited about this kind of project and really hands-on, they took their feet off the desk, because summer's always the time to take off, like I said, and they started really getting into this project. And what you started to see is the forecast discussions themselves got a lot more detailed than the typical summer that you would expect. Graphics started to get a little bit better as our confidence grew, so I think they really appreciated getting their hands dirty, so to speak, in a project like this, and I was really glad to see that. Very motivating for me. So what you might have is something like a midnight pop, and then with that same graphic there, you'd see an updated pop where we were confident enough to start raising it. And you may raise it 10 or 20 points, percentage points, but you didn't. We're not talking about changing it from 30 to categorical or anything like that, but just making these little bump and pop to see if we can really get it. And you talk about the bump and pop, but there's also an idea of maybe lowering it in other places where that convective initiation wouldn't occur. So from a decision support standpoint, with millions of outdoor activities over the summer in the southeast, you can see where this may be a little bit more beneficial than something that's very standard. We create the standard back in the day when we would do this AFM. We would create this special AFM that would compare the POP to the EPOP, so it was easy for us to go in there and grab and make a statistical analysis of how we had to do it. Another suggestion too is, I don't know how many of you guys actually invest in the NOAA Hollings scholars, the students from the universities. We invested heavily in that to help us create this analysis. So somebody would the student would have to go in by hand and county by county make a yes or no determination as to whether convection occurred in that. So that had to be done every single day of the summer. So painstaking for somebody, but that was the part of their summer project. It really helps. So I would suggest you invest in a Hollings Scholar if you ever want to do any kind of project like that. It really helps big time. So I just sort of zoomed in here, but you can kind of get the idea of what a POP and EPOP and how we grab the statistics. Don't remember too much about my point here. I think it was just that verification of that earlier thing. So I'm kind of running you through the whole day. So we would analyze these boundaries, we put out the graphic cast, we make this AFM, and then somebody would have to go in here and sort of look at these images and sort of make a determination as to whether these things verified as far as our POP was concerned. This is what a typical spreadsheet looked like. I think I just pulled this one from the summer of 2012. We would have a number of CI or convective initiation locations by date, what kind of boundaries they were. And then I had them do something else too. I wanted to get a sort of a 1 to 10 kind of scale of how much they use these particular products, like what did they use to analyze these boundaries, radar, satellite, how did they find them, surface analysis, and then take some detailed notes so we can sort of get an idea of what products were the most useful in identifying these boundaries. It turns out that from our updated POP skill scores, outside of a few days here that go into the negative, which means the midnight shift won the forecast, for the most part, we outdid the midnight shift forecast on almost every single day across 2 summers. Not to mention climatology. Very difficult, by the way, to build a summertime climatology for a POP. That is a very tough thing to do. But we finally got some guidance on that and worked through that. And we beat POP climatology and sometimes destroyed it in some cases where we completely 100% difference between climatology and what we did here. So this is, again, a percent change in what we did. And we basically beat it every day but about 4 over 2 summers. As far as that product usage, I wanted to see what that looked like as well. So this is kind of a stoplight graph here. It's a little bit hard to read maybe, but at least for our sake, the satellite was heavily used. In other words, they rated the boundary identification 7 through 10 highly usable with radar and satellite and the surface analysis as well. So that was good to see. So satellite didn't even show up with low usage. Every time the satellite was used, the satellite data was used, it ended up getting very high marks as far as being a useful product in this particular project. And again, we went for that verification again. Every time a satellite image, this is on the back row here, is every time we use a satellite, how many times did it actually verify? And you can see here the verification numbers were very good. In other words, when we identified a boundary with satellite, 57 out of 69 times it ended up being convective, like we had hoped. Finally, number 4, this is sort of a wrap-up, and then we continue this on to today. We made it pretty much, we took it from the experimental mode into operational mode. The graphics are gotten much better. In fact, this is what our graphics from this year look like themselves, so we're able to hone in on these areas a little bit better. Made for a very nice product, very popular with our decision support in the summertime. People, like I said, there's so many outdoor activities, and to be able to give somebody something a little bit better than a climatology POP was very good. So you may inherit something like this as far as a graphic from the overnight or the next day, or this may be through something like 10 a.m., like this graphic here is the POP through 10 a.m., and then from noon to 9, we may be able to enhance that. So if people have outdoor afternoon or evening activities, they may expect a little higher POP in these particular areas based on those boundaries that were identified. want to kind of run you through a couple other examples. We talked about the ridgetop stuff, so you can sort of see this ridgetop here that extends from southwest to northeast across Alabama. You can see on some days that would certainly develop here, and you can see obviously the satellite would pick up on it well before the radar would. So those kind of conditions exist here that we've dealt with. This is another interesting one too. It's convective here. You can see the metro area here of Birmingham. The heat island, sort of a heat island effect. You can sort of see this convective initiation beginning here. Anybody want to guess? I guess everybody's on probably mute, but anybody want to guess what these little holes are? These are all like lakes and rivers and things. I sort of circled those here. So there's definitely something to this, okay? It's not just in vain that we were doing all this. There's a lot of interesting characteristics, at least to the satellite perspective, that you start to pick up on. So in other words, again, I don't want to be a broken record about this, but you go from a situation where the forecasters are sort of hem-hawing summertime weather and not really getting into it. And once you start to get into these products like the radar analysis here and the satellite analysis, you start to see a lot of interesting features that really are highly dependent on where that convective initiation is beginning or would begin with these little micro kind of boundaries around that are floating out there. I'm sure a lot of you guys have that as well. There's also the idea of having this differential heating impact. So in other words, you have another sort of like a ridgetop situation where you have an area that heats up faster because of early morning cloud cover or fog or something like that. Obviously, in the satellite would be an obvious go-to product to sort of pick out these differential heating kind of boundaries that definitely exist. We'll do some side-by-side. Again, I don't know how good your bandwidth here is, but you can obviously we know the difference. But Go 16 this past summer really was a big game changer in two ways. Obviously, the spatial resolution is a tremendous help when picking out these little fine-scale features, and the temporal too, because a really big way to pick these out is when they're moving. If they're moving in the mornings like this, you can sort of start to pick out where they'll end up and sort of time them out to where the maybe a peak heating of the day would occur, and sort of helps you with your forecast perspective. Also, one other key component too, and that was a lot of times with GOES 13 versus 16, we had to wait till the sun came up or use some kind of low light viz because the coarse resolution of the infrared products were just not quite good enough to pick out these little fine scale features. And so with the 1 kilometer now infrared, it made some identification a little bit easier before the sun came up, so we could potentially start to pick out these things instead of waiting on some kind of forecast update after the sun came up. We could potentially, and this is something we'll be exploring, we could potentially have an update or some kind of better forecast product before the sun even came up. So that's something we'll be exploring in coming summers. Just another quick example here of how interesting the summer weather can be around here. So sometimes you even start the morning with convection, which will create a boundary that later convection would fire up on later that afternoon. So you see here even the sun come up, some overnight convection that may lead to that as well. So it's just an interesting side-by-side between the 13 and 16. I think I just zoomed in on some of that here this morning, just kind of give you an idea of how complex the morning may be with fog up here in these valley areas next to ridgetops up here in North Alabama, while you have differential heating boundaries. But you guys have all seen this, nothing new here, but just kind of interesting perspective. The satellite's always been a very unique thing to look at, especially as the sun comes up. So the takeaways really from this project was, the summer weather was a lot more complex than we originally thought. That model that you have in your head about how the summers are supposed to go, climatology speaking, or like we talked about in this 90 and 70 and 30 forecast that we put out every single day, that didn't really come to pass. We started to realize how complex it really was. Maybe not so much in terms of severe weather or something you have in spring and fall or winter weather kind of thing, but it certainly was a lot more complex than that idea that we had. forecasters had a big appreciation because they were able to get really intimate with our weather here across the CWA and really across the entire Southeast. They really invested a lot of time in the weather, a lot of time in hand analysis, a lot of time in understanding the instruments and what their capabilities were, and also taught you a lot about geography of the area as well, and how the geography really impacts our weather. Those 16, like I said, is a game changer because of the temporal and resolution changes. You guys all know that. And, I guess as a final note here, I would to say to continue to be creative as far as our idea of going forward and how science and forecasting sort of impacts the IDSS. Sometimes I think it's easy for us to think, well, our jobs are going to be to use a forecast builder or something, a national blend of models for our forecasts, and all of our stuff is going to be in IDSS. But really, the science is the ground level to a lot of this IDS services that we have, and I think that's where we can bring about some positive changes. I guess if you have any questions about the project, or if you want any more information about it, you can always contact me, of course. And I think that's about it. Scott.
Thanks. I just have one comment. Infrared is 2 kilometer. I'd love it.
Somebody pointed at me when I said that. So you're exactly right. But I guess the improvement is what I'm getting at there.
Yeah, I'd love it to be 1 kilometer. That'd be great. So how does... I'm thinking if you're looking for a moist surface, I'm not sure if there's a channel you can use. I'm wondering if the 0.86 or the 1.6 can give you some information just as the sun comes up, because if it's really, really moist to the point of being saturated and flooded, the 0.86 and the 1.61 will give you some information, but I don't know how much.
Hi, Scott. This is Bernie. I'm going to jump in because and first I'll say thanks, Kevin. I thought your presentation was very good. I'm here from Sarah. And when you mentioned your one slide that you had areas that you circled and you said, what are these? Are they areas that were wet or areas that were water? That's one thing that will be an indication of a moist area, because it takes longer to either evaporate the surface and warm up and then be more applicable for creating convection. So that's one way to look at a moisture thing, by just inference. You think of that, how long does it take to evaporate the moisture from the surface so you won't have clouds forming over it?
Yeah, that's a good point, and you'd see that, but, at the point that you get to that convective initiation process where those clouds start, that's really almost too late as far as the forecast process. So, like you said, if we had some kind of product that could be generated earlier on that we could see, say, even before the sun comes up.
There is a land surface temperature baseline product that is in AWIPS from GOES 16. Okay. So that might be something to start looping into this project, where you're looking at the temperature at the surface and seeing where it's warmer and where it's colder.
Sounds good. Actually, what we did before we had that information available to us, we would actually go back to the previous day and see where the convection was to try to pick out, because, summertime convection usually have a lot of heavy rainfall,
right,
an inch or more, and we'd actually circle those areas from the day before, and that would be our indication of where those boundaries would set up. So.
Yeah, and that's what that sport product was, too, for the previous day's precipitation.
Correct.
Yeah. Any other questions?
Hey, Kevin, did you all look at the split window difference this past summer very much to try to detect moisture boundaries?
I'm getting a lot of negatives in the room here, so I'm thinking that they did not explore all those things. I think that's really probably something that we need to invest a lot more into going forward, is especially once GOES 16 becomes operational, is trying to figure out which, that may be the next logical step in the project, which products from the GOES are very useful, I think. So we can do a follow-up at some point with what we found from that. That's a good thought.
Okay. Yeah, I've noticed a few times. This is Chris in Huntsville, by the way. Noticed a few times this past summer when it's called the split window difference, or maybe the moisture difference, but it's like 10.3 minus 12.3, or reversed in some of the RGBs. But I've noticed, and this is just anecdotal, but I've noticed a few occasions where it seemed to indicate areas where there was boundary layer moisture pooling, and then subsequently convection seemed to be favored in those areas. But it's something that would, really deserve some kind of a study.
Okay. Take a note on that. Thank you, Chris.
Sure.
Any other questions for Kevin? Going. Well, thank you, Kevin, for the presentation.